So Jagjot is a DFT technology enablement architect for the Tessent products at Siemens EDA. She has over 18 years of experience in DFT, working with a wide range of products that spanned cellular, server, graphics, networking, and aerospace designs. So she has a very wide breadth of experience. So today, Jagjot will be talking about how to optimize Tessent Streaming Scan Network and how to determine the optimal bus configuration. So let's welcome Jagjot.
Good afternoon, everybody. So the only person standing between you and your drinks is really me. I hope I can still keep you all excited, and thanks for sticking with us throughout the day. I hope you still have energy for last 35 minutes, and I hope I can make those last 35 minutes worth your time. So SSN, Streaming Scan Network. We have had a ton of traditional presentations about SSN, wherein we talk about the value of SSN, how it helps optimizing test time, total test time, and test data volume. This presentation is really going to be a little bit different, right? We usually tell you there is a magic that SSN does to give you the most optimal test time and test data volume. I am going to introduce you to the magic. Once you know the magic with the math and the numbers and you start understanding the magic, then probably you can exploit that magic to give you the best results, right? So this presentation is really going to be focused on that. And so I'm Jagjot Kaur, Technology Enablement Engineer for Tessent family of products at Siemens. And I would definitely like to give special thanks to people who were in the background helping me with the presentation, Peter, Wojtek, and Amer. And now let's just dive right into our presentation. So SSN really is a data delivery mechanism for testing your cores in a retargeting group for hierarchical test. But now what makes that streaming scan or that data delivery mechanism stand out, and what makes SSN differentiated? I would like to touch base on a little bit of concepts about throttling, a little bit concept about what really is a packet before I start diving into the numbers and boggle your mind with the math and the calculations. So the motivation behind, I'm going to be considering this example which uses 19 cores, and these 19 cores are being retargeted in a group for hierarchical test. So let's spend some time on this slide to understand what are the limitations that traditional hierarchical test poses given this kind of a configuration when we are trying to retarget these kind of 19 cores in a group for test. So I would like you to focus, out of these bunch of numbers, I would like you to focus on really the chain length, pattern count, and channel count here, right? The simplest definition of test time is you multiply your chain length with your pattern count, and that's really what gives you the test time for a given core. Now, if you in traditional ATPG, what really happens is how you calculate, if you bring in your streaming scan network or this packetized delivery mechanism, how would a packet really look like? The packet should really compose of it should really be the sum of the number of bits of the EDT channels of each of the cores being targeted, right? It's as simple as that. So if you look at the channel count, and if you sum up the channel count for all of these cores, it is going to be 182. And that's what makes your packet size look like 182. But then another thing that I also need you to focus on is, if you look at this configuration, if the packet size really was 182 and you were using that packet size, you see that core G, something happens with core G, wherein core G ends up finishing last, whereas if you focus a little bit on the bottom side of the slide for cores P, C, and Q, they finish testing really, really quick. So now your packet is 182 bits, and some of the cores have already finished testing. So the rest of the data that they're receiving for those many cycles, they're just waiting for core G to finish testing, right? So now this is what differentiates SSN. In traditional ATPG, where core G taking the longest time for finishing its test, it really becomes the pole. It becomes the bottleneck which is driving your total test time and test data volume. But then what does our packetized delivery mechanism do to reduce this orange portion of your slides, which really are the number of wasted cycles, right? So I'm going to have you remember this. The takeaway from this slide is packet size with traditional packetized delivery mechanism should really be equal to the sum of the EDT channels of all the cores being retargeted in a group, right? So the packet size is 182. I want you to take away this number from the slide before we move on to the next. Now, the limitations that we really figured out, if I go back to my previous slide, here I said core G really becomes your long pole, right? So two terms that I want you to take forward is long pole and packet size here, right? So looking at long pole, core G really becomes your bottleneck that drives the total test time and the test data volume for finishing the test, right? It's a very simple concept to understand from the diagram that we saw. Now let's get a little bit into the mathematical expressions. So the wasted cycles, that orange portion on the previous slide, that really becomes the long pole cycles, which were the cycles being taken by core G, minus the optimal cycles. So if I have to go back, I'm sorry, I'm doing a little bit back and forth because I forgot focusing on this one. If you look at the bottom bar on the slide, that's the optimal cycles, right? If every core was given just enough data to finish their test almost at the same time, then the bottommost bar becomes your optimal number of cycles that should actually have been invested in to get the best benefit of SSN, right? So that's where we got the motivation of bandwidth tuning. And now if I have to look at the wasted cycles, that really is the difference of the long pole cycles minus the optimal cycles, that last bar in the diagram, divided by the long pole cycles. And in this particular example, the wasted cycles is 58.38%. And if you look at the wasted data volume, that is around 140%. So we end up using 140% more data than was actually required for testing these cores under test. Now, I want you to focus a little bit more at the bottom expression of this slide, where I'm talking about how the long pole cycles are really calculated, right? We talked about the test time for any core is a simple expression, channel length multiplied by pattern count, right? Now, bus width is another factor that gets introduced in the picture, because if your packet size is 182, it really, how many bits you are going to be delivering to your design is really now dependent on what is your bus width. If your bus width is not 182, then this whole long pole cycles get multiplied by another factor, which is your packet size by the bus width. In my particular example, the bus width that I am taking is 32. That means you are reserving 32 input pins for your SSN bus and 32 output pins for your SSN bus. But as DFT engineers, we all know that pins are an expensive resource. Test time is an expensive resource, and so is the test data volume. And as a DFT engineer, we all spend our life just focusing on doing multiple inventions, writing multiple different papers, saying, oh, I reduced test time by this, I did this magic or that magic, right? So the focus here really comes on, now, can you reduce the channel length for a given core? Of course, we can, and that's why the concepts of compression came into being, right? But pattern count, if I'm targeting really high coverage for my cores, I'm not going to be able to reduce pattern count beyond a certain number. Bus width, once you have dedicated pins for test in your design, pretty much all these three factors become fixed factors in your equation. So what is it that I can do? What is the magic that I want SSN to do in order to bring down the test time for me? And that's what puts our focus on packet size. Packet size is something that becomes a variable factor in my equation that I can play with. And looking at the simple math, if I can bring down this numerator, if I can reduce the packet size, I'll be able to reduce the total test time that is going to be invested in finishing the test for this particular core. Now, but in order to understand how am I going to be adjusting, how can I make this packet size smaller, right? If you remember the first diagram wherein I showed you wasted orange cycles, if I can start giving more bits to the core which needs more time for testing, and I can just give lesser bits to the core which do not need a lot of time to finish their test, I'll be able to bring down the packet size. So by the gods of SSN at Tessent, this diagram has been the most effective explanation of how we do bandwidth tuning, right? Give the most water to the biggest bucket and give less water to a smaller bucket, right? It makes this pictorial representation makes understanding the concept of bandwidth tuning very, very easy. Now, if you look at, and that's where we introduce the concept of throttling. By throttling, what I mean is I will control the number of drops of this water falling in the bucket according to the size of the bucket, right? That's where we introduce the concept of throttling. Now, how do I control how many drops go in a bucket? And that's where the magic of the tool lies. And this factor, which controls how many drops are going to fall in each of these buckets, where drops is the bits being delivered to your core under test through the packet, and bucket really is the core under test, right? I will call it throttle level for the rest of my presentation. So from this slide, I would want you to pick the term forward, throttle level, right? So Tessent, the magic of Tessent lies behind controlling how many bits, how many drops of water will go in the bucket, right? Now that means Tessent must have the knowledge of how big is the bucket and how many drops does it really need, right? So that's where the throttle level comes in picture, and let's now focus on what throttle level means, right? So SSN, as I said, controls the throttle level for a given core, and based on the throttle level, we will adjust the bits needed for each core in the packet. Keep correlating it with the water and the bucket. I am controlling the number of drops falling in those buckets of water. Now, so the throttle level of the core really, when we talked about the long pole, the term that we carried forward from the first slide, long pole, which was core G. So that does mean that core G, everything has now to be decided with respect to the longest pole in my design, right? If my longest pole needs this much time, with respect to that longest pole, I probably need this much time. So this brings in the equation of the max packets needed by the longest pole in deciding the throttle level for that core, right? How many bits do I need versus how many bits does the core with the longest test time needs, multiplied by, of course, the number of EDT channels of that core, because that's how your core is, interacting with the rest of the group under test. So now packets we already discussed, but I also want you to remember this. The packets is chain length multiplied by the number of patterns for the core being targeted for test. Now, if I have to put my focus back on this picture that I showed, right? Look at core G. Looking at core G, it needed 7 bits in the original packet. If no magic was done, SSN wasn't doing throttling, it wasn't doing any bandwidth tuning, it needed 7 bits in that packet, right? But look at core C, which needs, before core C, we will discuss the throttle level for core G, right? So core G, it's chain length times number of patterns divided by the max packets needed by the longest core, which in this case, again, is core G. So the throttle level becomes 1. That means, because this is the longest core, I'm going to supply it all the bits I can. So that really becomes equal to the number of bits of the EDT channels for that core. If it can receive 7 bits, I'm going to give it 7 bits. But look at core number C here, right? Core C does not need too many bits. It's the smallest bucket needing probably a single drop of water. But I'm still putting 7 drops of water in that with traditional ATPG, right? We are not going to be doing that anymore. So if you look at this, Core C was also using 7 bits for its testing. But with throttling in picture, what is Core C going to do? This is where the magic of SSN begins, right? This is the magic with the numbers that the tool is doing in the background in order to decide which buckets receives how much water. So for Core C, really, now the throttle level becomes its chain length times its number of patterns divided by the maximum packets that were needed by the longest pole, and the longest pole was Core G, right? So the throttle level really becomes 1 in this case. And what was the traditional ATPG or traditional data delivery would have given that core in that packet? 7 bits. But I have brought down those 7 drops to only 1 drop for that packet, right? And that's where the concept of throttling is. And now the new packet size, remember from the first slide we were talking about, if I can reduce the packet size, I can bring down the total number of test time or the test cycles, right? So now my packet size is dependent on, we said, the number of bits required by each core. And now we are reducing the number of bits required by those smaller buckets. And if now I take the sum of the newer bits required by each core, that becomes my packet size or a throttled packet size. Now if I have to go and look at the newer packet size, it really is the sum of the throttled bits of each core. Now, looking at if I apply this formula to all 19 cores, my new packet size really becomes 82. Does anyone remember what was the original packet size that I asked you to take forward and keep in your mind from the first slide? 182, right? So we have brought down the packet size from 182 to 82, and that's where the magic begins, right? Your long pole cycles have really been reduced. Now the chain length is the same, 500, packet count is the same, 4,000, but the packet size is reduced from 182 to 82, and of course bus width, the number of pins are still reserved for test. So you have brought down the total number of long pole cycles, right? Now if you understand this math and the magic, it enables you how to still group your cores in the most wise manner to be able to exploit SSN, and that's what we will discuss in some of the next slides with more math, more formula, and more numbers. But remember, towards the end of this presentation are the drinks waiting for you in the other room. So keep focused. So with bandwidth tuning in effect, if you now look at the cores, I only want you to look at these numbers, right? After applying all of that magic of throttle, the bits per core, which earlier were equal to the channel count, for core B, it came down from 8 to 4. For core C, it came down from 7 to 1. For core G, it is still 7 because it needs maximum bits or maximum time to finish its test. So I'm going to keep supplying it maximum number of bits. So I'm going to be controlling the water dropping in those buckets so that the buckets almost fill in at the same time. Remember those childhood riddles that we used to solve? Give me the best possible iterations that all of these buckets will fill at the same time. SSN is pretty much latching on those childhood puzzles, really. So now going to savings with throttling enabled, right? The formula still remains the same. Cycles needed for core G, or the long pole that we already talked about. So the savings really are, according to the new packet size, the wasted cycles, which earlier were 58%, that orange portion of the bar graphs, it has now reduced to 7.64% just by working on that packet size. If you understood the equation, you knew what was in your hands to play with, right? And the wasted data volume has reduced to 8.27%, which was earlier 140.30%, right? So now let's call these new long pole cycles. I'm not going to be using this long term long pole cycles. I'm going to be calling it calling it cycles throttled, right? Because this is a result of throttling. So throttling gets its name to be attached with the max cycles. It becomes cycles throttled. And now I'm also going to be calling the factor chain length times pattern count as the max cycle count, right? Because that was Core G's max cycle count was its number of patterns 500 by 4000, and that's the max cycle count, right? So now the cycles throttled, if you look at bullet 1 and the last bullet of your slide, the cycles throttled really is max cycle count times your new packet size by bus width, correct? We are just giving it a different terminology, math remains the same. Now zooming in a little bit more on the cycles throttled formula, which we ended the last slide at, right? So cycles with throttling, I already said that it's max cycle count times throttled packet size, which is your new packet size, 82, and bus width, right? But what if the packet size is less than bus width, right? People would say, oh, if I bring in the if I make this multiplier throttle packet size by bus width less than 1, oh boom, my test time is going to keep decreasing infinitely, right? But once you have reserved the bits on the tester for your bus width, that bandwidth is going to be consumed anyway, right? So you are not going to be able to bring down that factor even if you choose to do some wise calculations, make your packet look really small so that your factor becomes less than 1, your bandwidth is still getting consumed because those many pins are reserved on the tester. So that's why when we talk about throttled cycles, another thing that gets added to this equation is max of the throttled packet size by bus width and 1. I am not going to be able to use 0.75, 0.5, 0.25 because the bus width is reserved, right? And the data volume really is throttled cycles times the bus width. Now I need you to take this forward from this slide because this will be used for the next slides. And now if we look at the throttle level and the calculations that I did, zoom in here. The ideal number of bits per packet, right, where we multiplied it with the channel, the cycles needed by the core by the max cycles needed by the longest pole core times the EDT channels. Some of these numbers, the ideal number of bits per packet were 4 for core B, for G it was 7. For some, it is a fractional number. It's not really a whole number, right? So am I leaving something on the table unused with throttling enabled? In this particular case, not really. Because if you look at 0.924, I cannot provide 0.924 bits, so of course I have to go with 1. If you look at 2.6, I cannot be providing 2.6 bits in a packet, so I have to of course go with 3. So no, I'm not leaving too much unused on the table even with throttling enabled, correct? But let's consider some extreme cases. And this is where a lot of our customers, they come back to us, they say, you guys promised us the sun and the moon, but after enabling SSN, my test time just became worse. And this is where I'm going to be discussing how that becomes worse, because when you don't understand the magic, you're never going to be able to appreciate the magic, right? So this is where we start understanding that. And now we will be considering some extreme cases. I'm going to consider a smaller example, okay? But what's extreme about this example? I'm just using 6 cores, simple. It doesn't look rocket science, but I'm calling it an extreme case. Let's see how it's extreme. I already got a 10-minute pointer warning. So throttle packet size, if you see, is very close to the bus width. I already said, if you make the packet size smaller than your bus width, you're not really gaining anything. But here in this particular case, your packet size has become smaller than your bus width. Okay, that's fine. We are not forcing you to add more. But okay, let's stick with that number 15 by 20. That's okay. Number less than 1. Now the max of the test time for all the small cores, if you look at core B, C, D, E, and F, the test time they require versus the test time core A requires. Core A is orders of magnitude higher test time requirement than cores B, C, D, E, and F, right? So look at this, only 102K cycles, whereas core A, I just made up some hypothetical numbers for explaining this to all of you. But core A needs 10 million cycles, 100K versus 10 million, makes it extreme. Now the smallest cores, core B and C, if now you look at that, they also need, I already talked, they need only 1% of the time as compared to core A. But also for cores B, C, D, E, and F, we talked about throttle level, right? So now look at the throttle, the ideal bits that were required for some of these cores, much less than 1. It's not, we are not talking about 0.6 or 0.7 versus 1. Now we are talking about 0.08 versus 1. The core did not even need 1 bit, nowhere close to 1 bit, but I am still reserving 1 bit for that core, which does not need that 1 bit in the packet. But, so does that mean even with throttling enabled, I'm still leaving something on the table because my throttle level is not allowing me to deliver less than 1 bit for a core, right? So now, the conclusion about this slide is, I want you to focus on the throttle cycles really become, as I said, they are driven by the core with the maximum test time. Here in this case, it's 10 million, right? And times the throttle packet size, the packet size is 15, that blue circle right there, and the bus width is 20, and the max of 15 by 20 and 1 is 1. So really your new test cycles or throttle cycles is 10 million cycles. Now let's see if I can, going to the next slide. So what can we do in such a case, right? The case is extreme, you told me the problem statement, but what's the solution? You are EDA vendors, give me the solution, right? That's what we are here for. So in such a case, can I separate the long pole core? Can I separate the core A, which is using 10 million cycles? And can I add more cores to the mix of the cores being tested? We already said that, you know, the packet size is 15, bus width is 20. You're reserving that bandwidth. So why not use that bandwidth, right? So let's see, can I do one of these two? Can I do both? Or can I do none? Let's evaluate that. Now, we will see the impact of separating core A from the rest of the cores from that group, right? If I separate core A, the packet size really becomes the EDT channel width of that core, right? 10, which was 10. And the cycles core A was taking for its test were 10 million cycles, correct? Now, I just took out that big bucket from my group of buckets which were lying in that. I'm not going to wait for that big bucket. I will just deal with my smaller buckets and let them all finish soon, finish together, and big bucket, okay, it can deal with its own story, right? So I'm separating out the big bucket here. But if you now look at the new max for the rest of the cores left, right? The new max is really the test time for core F, which is 250K cycles. Let me know, guys, if the math becomes too much. I've tried making it very simple to keep you all engaged, right? So then, with the new max reducing, you are still using the same multiplier, which is your bus width by your packet size, your packet size by your bus width, but the factor that gets multiplied by it, the new max cycles, I have reduced that factor. And now the cycles required for testing all the cores is 400K, and the cycles required for testing core A were 10 million cycles. If you add these up, I am looking at 10.4 million cycles. But what was throttling giving me in the previous slide? it was still giving me 10 million cycles. We are evaluating, can I separate core A from the mix, and can I see some good results? So if you see here, even with after separating core A from the mix, you are still having 10 million cycles with throttling, and 10.4 and 10.4 after separating the core, right? So what's the conclusion here? The conclusion is throttling is still beneficial, and no additional benefits of separating a core when your bus width is less than your packet size. You're already keeping unused bandwidth. So just add more cores to the mix, fill that bandwidth to increase the utilization of the bus that you are already reserving on your tester. But now let's say you had much less number of pins available or reserved for test. Your bus width was not 20, which was my previous example. Let's say your bus width was just 10. Let's see how this equation, the same thing plays with the same cores, right? Now the effects are, the ratio of the throttled packet to the bus width becomes 1.5, right? Your bus width is 10, packet size is 15, so 15 by 10, the ratio is 1.5. The ratio will, or the multiplier will impact the total number of throttled cycles. Remember this formula where we talked about this ratio, right? The ratio is going to impact my number of throttled cycles. So now, and the max cycle count still is orders of magnitude larger than the rest of the course. 10 million versus all the rest of the course. And this max cycle count then also plays in the equation of deciding your long pole cycle count, correct? So your total cycles now really become 15 million cycles because you are multiplying it by a factor of 1.5, right? So now let's, for this particular example, when I reduce the bus width, let's see how separating of core A will impact the whole game, right? It changes the whole game. It changes how this whole magic works. So core A, which was taking 10 million cycles, I separated it out, still taking 10 million cycles, but the factor is 1.5. Earlier the factor was 1, right? So even if it was getting multiplied by the max cycles, throttled cycles, it wasn't impacting anything in the game. But now when my factor has become greater than 1, those 10 million cycles multiplied by 1.5 versus only 250K for the rest of the cores, the max of rest of cores is core F, versus multiplying 250K with 1.5, that changes the whole game, right? So if you now look at the cycles for all other cores are only 802, the 802K, and for core A are 10 million cycles. If you add them up, the total cycles becomes around 11 million, 10 million 802K cycles, whereas when core A was included, the cycles were 15 million because the multiplier is 1.5. So look at the percentage saving that I did by only splitting core A. I just released SSN from the shackles of bad core grouping, right? So if you release SSN and give it and pave the ground for SSN to run to give you the best results, it gives you the best results, right? So now if you separate core A out, you are going to be consuming only 11 million cycles versus if you throw core A in the mix for testing with the rest of the cores, which gives you 15 million cycles, right? Now with large designs, I talked about math, I talked about numbers. People will say, girl, we have got 500 cores in my design. I'm not going to be doing these calculations. What are you guys for? If I have to do these calculations, why do I buy SSN? Why do I use SSN? So of course, it looks complicated. Of course, math, no one likes math and numbers, but I do. And so any easy solution? The easy solution is we have something coming up for you guys, which is under development in our tool. The feature will be called hyper-throttling, which will solve these kind of problems for you all. And it will release you from the burden of math and number and calculations and formula, which not many like. Now, another question, Terry and Janie, just 2 slides. I promise, less than a minute. So another thing that we hear from the customers is, what if I start adding multiple SSN buses? Will I use less test time? Because customers, all of you are really smart. Our customers are smart, and therefore they are tough. They give us tough problems to solve. But at the same time, their creative minds sometimes creates pitfalls for them, and then we have to solve some problems. And it gives us creativity while our customers bring us pitfalls. So if most of the times people want to add multiple buses, because looking at the large size of the designs, the motivation behind having multiple buses is really physical implementation. People say, I cannot have your SSN bus running from the north side of my chip to the south right side of my chip. It's just too much burden on physical implementation. PD anyways hates DFT, and bringing in SSN into the mix, they want to kill us at the first sight, right? That's what happens. So having multiple SSN buses, if you apply the same fundamentals that I talked about, right? Having multiple SSN buses cannot be driven by the factor of I will reduce test time if I throw in more buses to the mix. No, the same equations will come into play. So having multiple SSN buses can be driven by physical implementation needs, but if you have that wisdom of the magic that the tool does with the math, if you keep that wisdom in mind, you will still be able to exploit SSN to get its most optimal results. So concluding on this slide, having multiple SSN buses cannot be driven by test time in mind. The only driving factor can be physical layout or physical implementation. But while you are trying to separate those buses, consider it, extrapolate the idea of multiple cores to multiple buses, right? If you now see what cores can be grouped and served by a bus versus what set of cores can be grouped and served by another bus, you will still be able to see very good test time benefits without you really crippling SSN and making test time and test data volume results look worse. So the summary really is the takeaways from all these slides. We started from the first slide where I said long pole. The big bucket is my problem child. How can I control that big bucket? Can I separate it out from my groups, or can I reduce my packet size to get to reduce the total number of throttled cycles? So the designs which have some cores with orders of magnitude higher test time than the rest of the cores do careful planning. I told, look at your bus width, look at your packet size, look at how that multiplier is going to play if you have an extreme core in the mix with the other cores being retargeted for test. And then such planning, of course, I said, is based on bus width, packet size, which were the 2 major factors contributing to that multiplier, which we kept talking about, and the relationship of the core under test, its test time, to the problem bucket, to the problem bucket child, right? Now, and then to conclude, hyper throttling, which is another feature that Tessent is coming up with. It will release you from the burden of even doing this kind of planning.